Hey there! In this video we are going to look at the basic tangent function. We're going to look at it graphically and make connections with the unit circle. We're going to look at it numerically with values in a spreadsheet. And we're going to summarize some of the main features of this function. Alright, to generate the tangent graph here, I have a set of axes where the horizontal values are marked off in fractions of pi for our angles, and the vertical axis is marked off as usual, integers as the scale, and I have the unit circle over here, just shifted over to the left a little bit to keep it out of the way. And what we're going to look at here is the values of the lengths of the segments here, or in other words the coordinates if this circle was in the middle, as we go around the unit circle, and then how that translates into the shape of the graph that we get. Now, this is best understood if you've already looked at how the graphs of sine and cosine are generated in this way. So if you haven't watched the video that I have for that, please do that first. So just like we did for the sine and cosine graphs, as we generate this, we'll follow what's happening in the unit circle, see the value of tangent represented visually here with the length of a line segment, and then it'll trace out the graph here. Before we trace out the graph, we'll just look at the triangle here so we get a sense of what tangent is and remember where it comes from in terms of the unit circle. So we'll just go here and stop somewhere there. The tangent of this angle actually involves both of these numbers here. The sine of this angle in standard position is the y-coordinate over the radius, and if the radius is 1, it's just the y-coordinate. Sine follows the y-coordinate. Similarly, cosine is the x-coordinate over the radius, but if the radius is 1, it's just the x-coordinate. Sine and cosine each only have to do with one of these two things. However, tangent is the ratio of these two. It's the y-coordinate divided by the x-coordinate. And so the tangent ratio involves both of these things. And as you saw at the start here, at the start the tangent is 0 divided by 1. So the tangent at the beginning is 0. So when we start plotting this graph, you're going to notice that there's a point right at 0. It starts there at the origin. All right? And I'm going to model it with this length of this purple line segment here as we go. So now as the angle increases here, you're going to see that it starts to go up, right? In a similar way to the sine graph did, because as the angle gets bigger, this is getting bigger, and so when you divide that by that, it becomes a bigger and bigger number. But since for tangent we're dividing these two, there's two things affecting that getting bigger. This is getting bigger, and when you divide things, the number on top of your fraction, if you will, the y-coordinates on top, it gets bigger. That makes the value bigger. But the x-coordinates on the bottom, y over x, if the x-coordinate starts to get smaller, that also leads to the tangent value getting bigger. And so as we go here, it gets bigger and bigger and bigger, and actually it gets up to there, and you can see I've stopped pretty close there to where it's about 1. It's about as close as I'm going to get to 1 probably, where this is 0.7, well it's 0.71, but more or less that value is 1 there. Tangent gets up to 1 when the angle is actually halfway across here, when that angle is 45 degrees or pi over 4. You know that that triangle is an isosceles right triangle, or in other words, these two lengths are the same, and so when you work out the tangent value, 0.7 divided by 0.7, right, is 1, and that's why that's 1. Now, one of the things that's different than sine and cosine is if we keep going here, this is going to keep going up, because as you see in the triangle, right, as we keep going here, now we've got it where the red value is bigger than the blue one, right? I've got it here where this is about twice as much as that, right? This is almost 0.9, 0.45, twice as much. That tangent ratio right now is up to 2. Tangent can keep going here. There's no maximum on this because I can keep going here like this, and I've got it up past 3 now. I'm going to go up here to about, well, I'm about around 4 there, right? Because this is now 0.97. It's about 4 times as much as that. In theory, tangent can go up as high as you want as it gets going higher and higher and higher here. So somewhere there now I've got 0.99 and 0.11. It's 9 times that. The tangent ratio is 9. Now this thing's rounding these numbers, so at some point it's going to snap to numbers that we won't be able to see what's going on, like it's rounded that to 1, even though it's slightly less than 1, and it's going to round that down to 0 pretty soon. But in theory, that's going to go up infinitely as you approach 90 degrees or pi over 2 from this way. All right. Now the thing that happens though is as soon as you get to 90 itself, like that, now it doesn't show it because it's rounding and it's still showing that line there. But if we think about it, the tangent at pi over 2, this angle here, it's 1 divided by 0. The tangent of pi over 2, you've probably seen that already before, tangent of pi over 2 is undefined because you got 1 divided by 0 here. On the other side here though, as you go to this other side, now this is still showing this as a positive number just because it's represented by a length on this program I'm using. But if this is the unit circle, that's actually a negative x-coordinate there, and the tangent on the other side, you see that this value of this line here, as soon as I cross that 90, it flips over to being a negative value, and you're going to see that this comes up from there because as I'm going there, this value is a negative, and if I have a positive number here divided by a negative, I have a negative. And you've undoubtedly seen before that when you're in quadrant 2, past pi over 2, the tangent is negative. And it is negative all the way up to when I get to the angle being pi right there, right? And now it's back to 0 for the same reason as it was at 0, right? When you're halfway around here at pi, you've got 0 over 1, so it's 0. And then that pattern just continues on here because now we're back to the same pattern we had in quadrant 1. In quadrant 3, the tangent repeats the pattern that it had in quadrant 1. If I keep going there, you're going to have, for the same reason, as soon as you get to 3 pi over 2, we'll see if it lets me stop right at 0 there, right at 3 pi over 2. So you've got 1 divided by 0. So the tangent is also undefined for 3 pi over 2. And then as you keep going, it flips over to the negatives again and then comes back here. So you just have this repeating pattern that looks like that. And every time you get to one of those points where the angle is vertical, it's undefined. And even into the negatives, the same thing here. If we go over here, this is going to continue down to here. That's going to be down towards negative infinity. But then as soon as you get down to that value, negative pi over 2, it's undefined at negative pi over 2. And then as soon as you're going backwards into that other quadrant there, now it's up there, hit 0, and so on. All right? That's what the graph of tangent looks like. Now we'll just get rid of that graph. And we'll generate that same graph again, but we're going to do it alongside the sine graph. I won't put the sine and the cosine just because it is going to get pretty crowded on there, but we can kind of think about how this works and how it compares. But sine and cosine have so many similarities that you'll get the idea of here and how it compares. So we're going to have both of these things modeled over here, and then we're going to have the graphs generated here as we go. So as we start off here, the graphs look pretty similar and those values look pretty similar, the length of those two lines. But pretty soon, the tangent kind of overtakes it. And the reason it overtakes it, it gets to 1 a lot quicker. And the reason is because for sine, you're doing this divided by the radius, the hypotenuse on that little triangle, which is 1. That doesn't change as you go around. Whereas tangent, you're dividing this same y-coordinate by this x-coordinate, and that does change. That gets smaller. The radius stays the same. So for sine, when you divide the y-coordinate by the radius, you're always dividing it by 1. Whereas tangent, you're dividing a number that's getting bigger by a number that's getting smaller, and thus it gets bigger faster. And then secondly here, tangent can get bigger than 1, and the reason for that is because, again, you're dividing something by something else here that's getting smaller. This can easily, as you can see here, be bigger than this. Whereas for sine, the length of that red, the y-coordinate, can never be longer than the hypotenuse, the radius there. At most, it can be the same when you get to pi over 2. When you get to pi over 2, they can be the same, which is why when you divide things that are the same, you get to 1 here. But it can never go above 1 because you can't have y-coordinate bigger than the radius. And if we were generating the cosine graph, it would be the same thing. You can never have the x-coordinate bigger than the radius. But for tangent, obviously you can. And so that just keeps going like that, as we just saw. And that's just roughly tracing it out with a few dots, of course. Another thing to notice here is, as you go along here, the sine graph and the cosine graph, it doesn't start repeating itself until you've gone 2 pi. The period for sine and cosine is 2 pi because that's what it takes for one complete cycle of the pattern to happen. It's going up to 1 in the positives, down to 0, still in the positives, and then into the negatives, down to -1, back up to 0. Whereas tangent goes up in the positives towards infinity, and then down from -infinity up to 0, and then it repeats right from there. The period of tangent is pi. The pattern repeats twice as often just because of the nature of what you're doing. Sine is positive in quadrant 1, positive in quadrant 2, then negative in quadrant 3, negative in quadrant 4. That pattern takes 2 pi to repeat, but for tangent it goes positive, negative, pattern repeats twice as often there. Now we'll look at the tangent function numerically here with the table and see some of those patterns and things that we saw graphically appear with the numbers here. So this is the angle that we're looking at in radians, and then it's going to be the tangent of that angle, the tangent ratio for that angle over here. So this is what we had on the x-axis of the graph, and this is what we had on the y-axis of the graph. Now I've got the angle in degrees here as well, because afterwards, to look at some of the subtle patterns around pi over 2, 3 pi over 2 that we saw, it's going to be easier to work with in degrees, but that we'll do in a minute here. So as we saw, the tangent ratio starts off for the angle being 0. The tangent ratio was 0, and then it started to increase like that. And then as we follow this down, right, if we go down there to 30, you know, the value is going up, 40 going up again. I'm going to put in here 45, and then I'm going to put in 50, right? We saw that at 45 degrees, or pi over 4, the value was 1 because it was that isosceles right triangle. If we keep going here, 60, 70, 80, right? That tangent ratio definitely goes above 1 and keeps getting bigger and bigger. Let's put in 85 for good measure there, 11. But you saw that if we actually put 90 in there, it was undefined. And so we get this result here. If we kept going, we saw what happened is now these were into the negatives on the other side. And so if we keep going here, put in 100, 110, and then we can fill that down to see the rest of it here into those negative numbers, into the negatives, and then back up to 0 like we saw on the graph. Now we're going to look at what's happening a little closer to this value of pi over 2, or 90, where we saw those values on one side go up, 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 and on the other side go down, down, down. So we're going to first of all highlight this row so we can focus on that. And then on one side here, we're going to start with numbers that are closer to 90 from below. So we're going to go, say, 87 degrees, 88 degrees, 89 degrees, 89.5, 89.9, 89.99, 89.999. As you get really close to 90, or in other words, really close to pi over 2, this is rounding it off, so those look the same, but they're not quite. They're just shy of pi over 2. These values do indeed get bigger and bigger and bigger, and we could put even bigger numbers in here. 89.9999, or even more than that, right? That's just going to get bigger now. Now it's 573,000. That's a pretty big tangent ratio. On the other side, if we take this and now we go from above, 93, and then 92, 91, 90.5, as we approach 90 from that other side there, 90.1, 90.01, 90.001. Those numbers are heading down towards bigger and bigger negative numbers, right? Now we're at that. We can match the other side by putting 90.0001, and then you see that that number, very similar to this number here, in that it's in the hundred thousands, right? 573,000. This is essentially 573,000. The discrepancy in the numbers from the top and the bottom is just about how the rounding is happening here. All right, so from one side we saw in the graph these values headed up towards infinity, and on the other side we saw them head down towards negative infinity, but at 90 that value is undefined. Now, before we leave the table here, we'll just compare with sine and cosine. But before we do that, we'll just continue this pattern so that we go every 10 degrees and we don't have those values near 90 there. And we'll bring it down to our bottom of our table there. And we go back up here now, so we follow these numbers. Right, sine starts at 0, cosine starts at 1, but those numbers you're going to see are never going to go beyond 1, and they're never going to, if we keep going here, they're never going to go below -1, right? And again, that's because these two involve the radius in the unit circle, the hypotenuse in that little triangle. The y-coordinate for sine can't be bigger than the radius, and the x-coordinate can't be bigger than the radius for cosine. So you see that they're never beyond 1 or -1. Whereas tangent, since it does not involve that radius, can get to be numbers that are bigger than 1 or smaller than -1, beyond those values that sine and cosine can. So we'll sketch the graph of the basic tangent function from what we've seen so far. And that grid looks more or less like what we had at the beginning with our software. The angles on the x-axis, the ratios on the y-axis. Now, as we saw, tangent comes from the two values, the y and the x. Tangent is y divided by x. And at the start, when this angle is 0, collapsed down there, the y-coordinate was 0. So tangent started at 0, so we're going to put a point there. And then as this goes around, tangent is also going to be 0 here because that's also where the y-coordinate was 0. So when you're halfway around, which is pi, it also is 0. And if you kept going, it's going to be 0 again there. Every time it hits one of these horizontals, that's when the y-coordinate is 0. So 2 pi, 3 pi, 4 pi, those are 0. And when you go the other way, negative pi, negative 2 pi. Every pi, the tangent ratio is 0. And then in between there, when we had the angle reach these verticals here, tangent was undefined at those points, right? I'm going to put a question mark there because it was undefined there for angles of pi over 2, 3 pi over 2, 5 pi over 2, and all of that. And the behavior that we saw for that, if we draw this first quadrant here, the tangent ratio started at 0. When we were at 45 degrees, it was 1. So I'm going to put that at pi over 4, that value, this is 1 here. So I'm going to put a point right there. And what happened is we saw that this was getting bigger and bigger and bigger and bigger, but as it approached pi over 2, it just kept getting bigger. So when I'm going to draw that, I'm going to draw this in here like this, and it's actually what you call a vertical asymptote. It has asymptotic behavior there because as you get close to pi over 2 from this side, that heads up towards positive infinity. But on the other side, as you approach pi over 2 from this side, those values go down towards negative infinity. We're going to draw that in the bottom here. I'm also going to put this value in here because similar to this, when we're at 45 degrees, or pi over 4, the value was 1. Well, the same thing is true over here. When this is a value here, a negative number and a positive number, when those are the same length, that value is -1. So we can put that point in there like that, and then we can draw this curve. This is going to follow that same thing down towards negative infinity there. It's going to be asymptotic that way. This line here, this line, I'm going to put a dotted line there because that line is a line that those two curves get closer and closer to, but don't ever actually touch that. Because at pi over 2 itself, right here, the value is undefined. There's no y value for that point. But as you get infinitely close from both sides, the graph goes up towards positive infinity on the left and down towards negative infinity on the right. You say that this vertical line here, which you can write as x equals pi over 2, that equation of that vertical line, is a vertical asymptote for this function. Now, every time on the unit circle you get to one of these verticals, right, that's where x is 0. So if tangent is y over x, when x is 0, that's when those vertical asymptotes are going to occur, right? So it's going to occur at pi over 2, but then also again at 3 pi over 2. So what I'm going to do is I'm going to draw that dotted line in there as well. At 3 pi over 2, it's going to occur again if I go another half turn from there at 5 pi over 2. They happen every pi, but they happen at the odd multiples of pi. 1 pi over 2, 3 pi over 2, 5 pi over 2. Right? Every time that the x-coordinate is 0 here, at these vertical points in my unit circle, which is kind of becoming a mess there, let's erase some of that, you have that asymptotic behavior there, where the graph goes both towards positive and negative infinity on either side. And just to complete this, 7 pi over 2, and then on the other side here, negative pi over 2, negative 3 pi over 2. So for drawing that graph, we're going to just repeat this same pattern again and again. I'll just finish this piece first here by putting that value. Just for the same reason that this is here, it's going to hit 1 there as well. And that just helps me get the shape of the curve right, so that I'm not drawing it like this, or that I'm not drawing it like this, right? To get that point halfway in between here and here, it's going to be at 1. All right, so I can just put that curve in like that. And as long as I roughly get it going closer and closer there, I'm going to put these 2 points in here because for the same reason as here, that pattern is exactly the same, and those points there, and the same goes here. Well, that one's off the grid almost, but that one's there. And then I'm going to draw it in one smooth piece here from there all the way up to here, because that's what that curve looks like, more or less. Same goes here, like this. Same on the other side here in the negatives. Put those points, draw the curves in. All right, so just like we saw before, one piece of the pattern from 0 to where it's 0 again, it's up like that, and then down in the negatives like that, and then that's just repeating. Or you can think of it as this is one piece of the pattern, and that just keeps repeating again and again and again. All right? Let's put down some of the important information down below, what we have for this function. We said that the period for that graph is pi. It's different than for sine and cosine. Sine and cosine, the period is 2 pi. This is half as much. The max and min, there is no max and min. No max or min. Right? Because the graph heads up to positive and negative infinity, there's no top or bottom, so it doesn't have a max or a min there. The amplitude, since there's no max or min, we can't really talk about the amplitude of the thing. So there is no amplitude, none. The domain is all the possible x values. For the sine graph, you saw that the domain was all real numbers. But for here, there are for sure some numbers that are not included, and where that is where you see these vertical asymptotes, where you see this asymptotic behavior. Or in other words, the places where tangent is undefined, all those odd multiples of pi over 2, 1 pi over 2, 3 pi over 2, 5 pi over 2, and so on, those values. So you could write a list for those if you want. You could say, let's say like this, negative 3 pi over 2, negative pi over 2, pi over 2, and so on, and writing enough down to get the pattern. So you can see the pattern. Maybe I'll put dot, dot, dot there, and this way as well. But it's better if you can write an expression for these rather than a list that goes infinitely long there. You may have written expressions like this before. More or less what you say is the first one of them, pi over 2, and any other one you can get by adding on multiples of pi. That one is plus pi, or this one is plus 2 pi, or you can get one by adding on negative pi, right, to get to there, or adding on negative 2 pi to get to that one. So you can say pi over 2 plus n pi. And what you need to say, though, is where I'm using n to be any integer. If n is any integer, didn't really leave myself enough room there, but you get the idea there. And now what we're saying, the domain is every number except that. These are the values that x cannot be. So you're going to say x cannot be that, and it's implied that you mean x can be every other number. The domain is every number except those. The range, on the other hand, if you think back to the graph here, the range, everything is covered here. All the y values are possible. Since this goes up and it goes down infinitely there, every y value, every value is possible as a tangent ratio for y. So what you can write there is you can say all real numbers. I'm going to put it with words. You can put it with symbols if you want, but I prefer this. And then asymptotes, you're saying where do those asymptotes occur? It's basically these numbers. So more or less you can say the same thing. We wrote one of them up here before. X equals pi over 2 is the equation of this vertical line. X equals something is the equation of a vertical line. So you can say that any of them you can obtain with an expression like this one, right? If you write an expression like that. So the equation of one of them is just x equals pi over 2, but you can get any of them by adding on multiples of pi. So where the same thing is true there. That expression gives you the equation of all of the asymptotes. And I won't write this again, but that applies here as well, where n is any integer. All right? So that's an introduction to the tangent function, why the graph looks like it does, graphically and numerically, and then some of the important features of that graph.